So after learning how to equip the camera for the data collection, how to set up labeling and label configurations, and how to create and customize the randomizer, we will see how we can collect, train, and validate data. So we will start collecting a large dataset of RGB images, the scene, and the corresponding pose of the cube. And then we will use this data to train a machine learning model or to use a model that has already been trained to predict the cube's position and the rotation from images taken by our camera. So we will then be ready to use this training model and go on. So in order to collect the data, actually a set of images with the corresponding position and orientation of the cube relative to the camera, we need to collect first data for the training process and then data for the validation one. So there is a training dataset of 30,000 images and a validation dataset of 3,000 images. And the numbers are exactly what they should be, 1 to 10. So we have one image for validation and 10 images for training. So we will select the simulation scenario game object, and in the inspector tab here, make sure that automatic iteration is enabled. So when this flag is enabled, our scenario automatically proceeds through iterations, triggering on iteration start method of all randomizers on each iteration. When this flag is disabled, these iterations should be triggered manually. So in the inspector view of pose estimation scenario, so go to pose estimation scenario, set in the inspector view of pose estimation scenario, set total frames here to 30,000. And then press play and wait until the simulation is done. Be careful, it will take about 10 to 15 minutes. So I will click start right now. And here you will see that the training, the simulation is being done. Here we have simulation, you'll see time in seconds, unscaled. We will wait a little bit. So here we are. At last, it has finished. Select again the main camera. And here is the inspector view. At the bottom of the UI for perception camera, you will see there are two buttons. There are buttons for showing the latest dataset output folder and copying its path to clipboard. So if you click, for example, show folder to show and highlight the folder in your operating system's file explorer, you will see that there are some folders right here. Here is the final one, and I will change this name to UR3 Cube Training. And inside these folders, you will see there are some subfolders, the dataset, and here is the log file, as you can see. And finally, we have another one with RGB and all these things. We have images for all these instances. So now we have completed the validation, the data validation. Now we can go on and train our deep learning model. But actually to train the model is something that will take many hours or days if you don't have GPU support to your computer. It will take about 5 to 6 days to complete this deep learning model. So what I suggest is actually using this predefined training deep learning model, and we will describe how it actually works. So more information about the training model and how to transfer domain randomization to deep neural networks from simulation to the real world, you can read this paper about the algorithm, the way this deep neural network is created. what is really important is to check the method. The method is that we try to randomize the aspects of the domain for each sample, for each image, using specific factors. First of all, the number and the shape of the structure objects on the table, then the position and the texture of all objects on the table, textures of the table, floor, skybox and robot, position, orientation, field of view of the camera, number of lights in the scene, position, orientation and specular characteristics of the lights, and type and amount of random noise added to images. This is the first thing. The second has to do with random RGB values, a gradient between two random RGB values, and finally a checker pattern between two random RGB values. These are the random textures that are chosen. So what we're trying to do is actually, this image is actually what we are trying to do, is to create a model by using specific layers. First of all, the input is an image with 224 to 224, and the output of the network predicts the exact coordinates of objects of interest. So first of all, it will take these images, then smaller one, smaller one, smaller one, until fully connected layers, which means X, Y, Z. So here are detection errors for various objects, because we always have errors in these models when we are trying to create models by deep neural networks. You will see that after trying to train our model, this is the pre-trained model, this is trained from scratch. So after thousands of images, then at last the pre-trained model and the one that is trained from scratch has exactly the same performance. So here are also two executions of grasping objects using vision learn in simulation only, and here you will see the results of this experiment. So this is a great paper that you can read more information about how domain randomization was transferred to deep neural networks in order to create the model. So now we will use our trained deep learning model to predict the pose of the cube and pick it up with our robot arm. So here you can see the first part is pose estimation model, or ROS, TCP endpoint, and move it motion planner. All these things are from the ROS side. So in the Unity side is the ROS TCP connector package. Here we have our robot, and the connection between ROS TCP endpoint and ROS TCP connector package has all these messages. First of all, the input is the RGB image from Unity, from the camera of the robot, to ROS. Here, this RGB image is used from the algorithm or for the pose estimation model to give the output for the predicted cube pose back to our robot. Then our robot gives to ROS back the motion plan request to predicted cube pose, and finally ROS gives the final message, the fourth one, that is the motion plan. How to move, where to move, and when to move. So here is the ROS node, here is the Unity package, and now we will see how we can set up ROS and use our pre-trained model in order to predict the right cube pose. So let's go now to our Docker desktop. Here we are. And now I will open PowerShell. Very good. Okay, so be sure that you download the Robotics object pose estimation, and then we will use Docker to create another image here and to use it for our ROS. So before going on, we will need to download and install the cmake command for Windows. So we will go to Google and we will write cmake Windows download. So here we are, download cmake. And here you can download the installer for Windows for 32 or 64-bit. In my case, I will download and install this one. The installation is pretty simple, as always, for Windows. If you have Mac OS, you can download this one, Mac OS 10.13. If you have one of the previous versions, you can find it right here. Okay, here we are, set up, next. I have already set up, but you can just select next, nothing else. And according to the question, if you would like to add cmake to your path, please select yes, that you would like to install cmake and add it to Windows path so that you can type everywhere in PowerShell cmake and you can use it. Then we will go on with PowerShell, but this time we will open PowerShell as an administrator. So right click, run as administrator. And here we are. Then go to the right folder. So in my case, I will go to users, my user, in folder downloads, robotics object pose estimation, and again the same. With dir, you can see the files in your directory. And here now, I will write the command, which is docker build the parameter t Unity Robotics pose estimation, the parameter f docker file. And be careful, we need here full stop. So docker build t Unity Robotics pose estimation. Very good, here we are. And I will hit enter. And building will be started. Everything is okay. Use docker scan to run tests again. Okay, it is okay, don't need to run it right now. I will start docker. So I will write docker run it. Be careful with two rm parameter p from 2000 from 10,000 to 10,000. The parameter p 5005 Unity Robotics pose estimation bin bus. And here we are, Katkin WS, and you will check that Docker Hub now here you have another instance with Unity Robotics pose estimation that already has been started. These are the previous one. This is the last one that is actually running. So we are ready. Docker is complete. And we will now source our ROS workspace. This means that our ROS workspace will be ready to accept commands. So I will write here source devel setup.bus, and now the ROS workspace is ready to accept commands. Now we will set up the Unity side, so I will go back to Unity. Here we are, and we will connect with ROS. We will work on the same scene as we did before. So I will go to Project tab right here, Assets, required assets right here, prefabs, and then part 4. And we will drag and drop the ROS objects prefab into the hierarchy tab right here. So drag and drop it. And then the ROS TCP connection needs to be created. So in the top menu bar in Unity Editor, select Robotics, ROS settings, and we will find the IP of our ROS machine. Actually, we are running ROS services with the Docker container. So in this ROS IP address, this is the one that we need. And if you are running ROS service, for example, in a non-Dockerized setup, you will have right here to override Unity IP and set the one that you have already set up. But in our case, these are right. We don't have to do anything else. Ensure that here ROS IP address is 127.0.0.1. Here we have 10,000. I will write here again the same 127.0.0.1, 5005, 10.1, and all the others are correct. So I will now close it, and actually opening the ROS settings window, we create a ROS connection prefab assets here in assets resources. Here we are. Here we have a ROS connection prefab, as you can see, with all the user input settings. Here are the input settings that we have created, and will be instantiated in the Unity scene, and the connection will begin automatically. Now, the provided script that is in assets, required assets, scripts, trajectory planner.cs contains the logic to invoke the motion planning services and the logic to control the gripper and the end effector tool. So in the trajectory planner script, you will see that there are two functions that are defined. The one is the invoke pose estimation service. So I will open it, double click. So here there are two main functions. Here you will see that the one function is the invoke pose estimation service, and the other is the pose estimation callback that creates a ROS service request and manages the ROS service response. So here we are, we invoke the pose estimation with this code, and here, if the response is not null, the position output by the model is the position of the cube relative to the camera, so we need to extract its global position. So we take the position, the estimated position, and the estimated rotation, x, y, z, and then we publish the estimated position and the estimated rotation, and we also print them to our screen. So we will close now the script and we will return to Unity. We will select again the ROS objects, publisher. So right here, ROS object, click, and then publisher, game object. And we will assign the UR3 publisher, and we will take this robot, UR3 with Reaper, drag it and drop it here in Robot. Then we will take the cube, drag it and drop it here to the target. And finally, we will take the goal, drag it and drop it right here. And finally, we need the scenario, so we will take the simulation scenario, drag it and drop it right here. We will go back to the simulation scenario and we will uncheck the automatic iteration right here. This is because we would not need anymore the data collection part, but if you want to collect new data in the future, you can always enable automatic iteration and disable ROS objects. So we will go again to the main camera, game object, uncheck the perception camera script component since we do not need it anymore, right here. And also note that UI elements that have been provided in ROS object canvas, where here we have the button panel, the position panel, we have the event system. That is, all these things are added by default in Unity. So go, for example, in ROS objects, canvas, button panel, right here. The on-click callbacks have been pre-assigned in the prefab, as you can see, and these buttons set the robot to its upright default position, randomize the cube position and the rotation, and also randomize the target and call the pose estimation service. So we will now need to put all these things together. So we will go again back to PowerShell, to ROS. We need to run the command in order to start ROS core, set the ROS parameters, start the server endpoint, start the mover service, start the position estimation nodes, and launch move it. So here we will write ROS launch UR3 move it pose s.launch, and here we are. As you can see, this launch file also loads all relevant files and start ROS nodes that are required for trajectory planning for our robot, for UR3 Robot. The launch files for this project are also available in the packages launch directory. So this launch will print various messages, as you can see, to the console, including the set parameters and the nodes that are launched. So the final message here, you can start planning now, confirms that everything is fine. So now everything is ready. We can see in the Docker we have the instance running. Here everything is ready to start planning now. And here we are back to Unity. I will click play. So here we are. I will click pose estimation, and you will see that it is capturing screenshot, waiting for service response, and here we are. And we can always click view service status and see all these things right here. And I will reset robot position, randomize cube, and pose estimation again. So here we are. First of all, we have to capture the screenshot. You see here all the details from the robot. And finally, our robot will go on, make the appropriate computations, take the cube, and place it in the right position. You will see how realistic it is, because when our robot went to its position, actually it moved a little bit the cube. And finally, so again, randomize cube, and finally click pose estimation. So here we are. Our project is finally ready. I hope that you enjoyed it, and thank you very much.